The universe expands, yet the truth remains, still within.
Is reality actually real? What if the world around you is not exactly what it appears to be? At first glance, reality seems obvious. You see objects, feel surfaces, hear sounds, and experience the passage of time. The universe feels solid, continuous, and stable. For most of human history, this intuitive picture of reality was considered accurate. The world was thought to be made of solid matter, moving through empty space, governed by simple laws that determined exactly how everything behaved. But as science began exploring the deeper layers of the universe, this comfortable picture started to break apart. Modern physics has revealed that the reality we experience is only a surface layer of something far stranger. At the microscopic scale, the universe does not behave like the solid world we perceive. Instead, it behaves like a strange mixture of waves, probabilities, and interactions that challenge our intuition. Electrons are not tiny balls orbiting atoms in neat circles. They exist as probability clouds, meaning that their exact position cannot be known until a measurement is made. In other words, before observation, a particle does not have a single definite location. It exists in many possible states simultaneously. This idea, known as quantum superposition, is one of the most fundamental principles of quantum mechanics. It suggests that reality at the smallest scales is not fixed, but instead contains many possible outcomes that only become definite when a measurement occurs. This leads to one of the most famous puzzles in science: the role of the observer. In certain quantum experiments, particles behave differently depending on whether they are being measured or not. One of the most famous examples is the double-slit experiment. When particles such as electrons pass through to narrow openings, they produce an interference pattern that can only be explained if each particle behaves like a wave passing through both slits simultaneously. However, when scientists attempt to observe which slit the particle goes through, the interference pattern disappears. The particle suddenly behaves like a localized object instead of a wave. The act of measurement appears to change the behavior of the particle. This strange result has puzzled scientists for more than a century. It suggests that the act of observation plays a role in shaping physical outcomes. Some interpretations of quantum mechanics propose that reality does not become definite until it interacts with a measuring device or an observer. Other interpretations avoid giving observation a special role and instead suggest that all possible outcomes occur simultaneously in different branches of reality. This idea forms the basis of the many worlds interpretation, in which every quantum event creates multiple parallel universes representing different outcomes. If this interpretation is correct, then reality may be far larger and more complex than we imagine. Every quantum decision could generate new branches of the universe, creating an unimaginably vast structure of parallel histories. Another surprising discovery from modern physics concerns the nature of matter itself. The objects we perceive as solid are mostly empty space. Atoms consist of tiny nuclei surrounded by electrons that occupy regions far larger than the nucleus itself. If the nucleus of an atom were the size of a marble, the electrons would orbit dozens of meters away. This means that most of the volume of ordinary matter is empty. The solidity we feel when touching objects does not come from particles physically colliding like billiard balls. Instead, it arises from electromagnetic forces between atoms. The electrons in your hand repel the electrons in the surface you touch, preventing the atoms from occupying the same space. In other words, what feels solid is actually the result of invisible forces preventing matter from passing through itself. The deeper physicists investigate matter, the more they realize that particles themselves may not be fundamental objects. According to quantum field theory, particles are excitations in underlying fields that exist throughout the universe. Electrons, photons, and quarks are not independent objects moving through space. They are disturbances in quantum fields that permeate all of space. This means that the universe may not be made of objects at all. Instead, it may be made of interacting fields. These fields constantly fluctuate, creating particles that appear, interact, and disappear. Even in the emptiest regions of space, quantum fields remain active, producing small fluctuations of energy that briefly generate virtual particles. Reality, at the smallest scales, is therefore not static. It is dynamic, probabilistic, and constantly changing. The mysteries of reality extend beyond quantum mechanics. When astronomers observe the large-scale structure of the universe, they encounter another puzzle. Most of the universe appears to be invisible. Galaxies rotate in ways that cannot be explained by the visible matter they contain. Something unseen must be providing additional gravitational pull. Scientists call this mysterious substance dark matter. Dark matter does not emit light and does not interact with ordinary matter in familiar ways. Yet its gravitational influence shapes the formation of galaxies and galaxy clusters. Observations suggest that dark matter makes up about 85% of the total matter in the universe. Even more mysterious is dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. Galaxies are moving away from each other faster and faster over time. Something is pushing space itself to expand. This unknown force has been called dark energy. and it may account for nearly 70% of the total energy content of the cosmos. Together, dark matter and dark energy mean that everything we can see, all stars, planets, and galaxies, represents only about 5% of the universe. The vast majority of reality remains unknown. This realization has transformed the way scientists think about the universe. Instead of a simple system of matter moving through space, the cosmos appears to be a complex structure containing layers of phenomena that we are only beginning to understand. Some physicists have even proposed that reality may be fundamentally informational. In these theories, the universe behaves less like a machine and more like a network of information processing. Space, matter, and energy could emerge from deeper informational structures that govern how physical systems interact. This idea has gained attention through research on black holes. When physicists studied the thermodynamics of black holes, they discovered that the amount of information a black hole can contain is related to the surface area of its event horizon rather than its volume. This surprising result led to the development of the holographic principle, which suggests that the information describing a region of space might be encoded on its boundary. If this idea is correct, then the three-dimensional world we experience could emerge from deeper information stored on a lower dimensional surface. In other words, reality might function like a hologram. Although these ideas remain speculative, they illustrate how dramatically our understanding of the universe has evolved. The deeper science explores reality, the less it resembles the solid and predictable world of everyday experience. Instead, the universe appears to be a vast network of interacting fields, probabilities, and hidden structures that shape the behavior of matter and energy. Yet, despite all these mysteries, science continues to advance. Each discovery brings us closer to understanding how the universe works, even as new questions emerge. The pursuit of knowledge reveals not only answers, but also deeper layers of complexity. And perhaps that is the most remarkable aspect of science. The universe is not just stranger than we imagined. It may be stranger than we can imagine. But perhaps the most fascinating part of this realization is that the limits of our imagination are constantly expanding. Every generation of scientists believes it has reached a deeper understanding of the universe, only to discover that reality holds even more surprising layers beneath the surface. What once seemed impossible often becomes the next scientific breakthrough. Concepts that were once dismissed as absurd have repeatedly become central to our understanding of the cosmos. Quantum mechanics, relativity, black holes, and gravitational waves were all ideas that initially challenged conventional thinking. Yet today, they are pillars of modern physics. The story of science is therefore not just a story of discovery, but a story of humility. Each time we believe we have finally understood the universe, nature reveals something unexpected that forces us to rethink our assumptions. The deeper we investigate reality, the more we realize that our everyday experience represents only a tiny slice of the full picture. Our senses evolved to navigate the world at human scales, not to perceive the strange behavior of quantum particles or the immense structures of cosmic space-time. In fact, the universe may operate according to principles that are far removed from the way our minds naturally interpret reality. Human intuition is shaped by daily experience, objects falling, surfaces touching, time moving forward in a steady flow. But the deeper levels of physics reveal a world where particles can exist in multiple states simultaneously, where time can slow down or stretch depending on gravity, and where the vacuum of space is filled with fluctuating fields. Even the concept of cause and effect becomes less straightforward when examined through the lens of quantum mechanics. At microscopic scales, events can occur in ways that appear probabilistic rather than deterministic. Instead of a single predictable outcome, physical systems evolve according to probabilities described by mathematical wave functions. The universe, at its most fundamental level, may therefore be less like a clockwork machine and more like a vast landscape of possibilities. This does not mean that the universe is chaotic or random. On the contrary, the laws of physics provide an extraordinary level of structure and consistency. The same equations that describe the motion of particles in laboratories also describe the behavior of stars and galaxies across billions of light years. The remarkable success of these laws suggests that beneath the apparent complexity of reality lies an underlying order that governs how the universe evolves. Yet this order does not always behave in ways that align with our expectations. Black holes, for example, challenge our understanding of space, time, and information. These extraordinary objects compress enormous amounts of mass into incredibly small regions of space, creating gravitational fields so intense that even light cannot escape. According to Einstein's theory of relativity, the center of a black hole may contain a singularity, a point where the curvature of space-time becomes infinite and our current physical theories break down. When quantum mechanics is applied to black holes, even more puzzling questions arise. Physicist Stephen Hawking showed that black holes are not completely black, but instead emit a faint radiation caused by quantum effects near the event horizon. Over extremely long periods of time, this radiation could cause black holes to slowly evaporate. This discovery led to one of the greatest mysteries in theoretical physics, the black hole information paradox. If a black hole eventually disappears, what happens to the information contained in everything that fell into it? According to quantum mechanics, Information cannot be destroyed, yet the evaporation of black holes appears to erase it. Resolving this paradox may require a deeper understanding of space, time, and quantum mechanics than we currently possess. Beyond black holes, other mysteries continue to challenge our understanding of reality. Dark matter and dark energy dominate the large-scale behavior of the universe, yet their true nature remains unknown. Experiments around the world are searching for clues about these mysterious components, but so far they remain elusive. This situation reminds us that the universe is still largely unexplored. Despite centuries of scientific progress, humanity has only begun to understand the deepest layers of physical reality. Each new telescope, particle accelerator, and experiment opens a window into previously unseen aspects of the cosmos. The future of physics may therefore hold discoveries that transform our understanding of reality as dramatically as relativity and quantum mechanics did in the 20th century. New theories may reveal hidden dimensions of space, deeper structures underlying matter, or entirely new forms of physical interaction. And if history is any guide, those discoveries will likely challenge our intuition in ways we cannot yet anticipate. Because every time humanity believes it has reached the limits of knowledge, the universe reminds us that the story is far from over. Reality continues to surprise us, and the deeper we look into the fabric of the cosmos, the more we realize that understanding the universe is not a destination. It is a journey that may never truly end. Still, within